classroom video. 3 tips before we start. You can always speed up or slow down this playback speed if that helps you get through the video. Second, you can pause the video at any time and catch up on your notes. Last, you can turn on the captions and watch my words go by on the bottom of your screen. Today's topic is limits and convergence, and we're starting our new chapter on differentiation, which is walking us into the realm of calculus. So let's get started. Here's our example. I have a person, perhaps you, and there's a wall over here, and you're some distance away from that wall. So the first phase, the first step is walk halfway to the wall. So we walked halfway to the wall. That's the first step. Now, the second step is repeat. So let's walk halfway to the wall again. All right? Third step, repeat. Let's do that again. So here we go, halfway, halfway. Here's our third step, halfway. Now, if we keep repeating this, we're going to get closer and closer to the wall. So here's a question I have for you. What is the limit? What is the limit of how far you can walk towards the wall by going halfway each time? So if you thought, well, the limit is the wall, you're right. Second question, will we get to the wall? Think about that for a minute. The answer to that is no. If we keep doing this, we're going to be like 10 to the minus 10 millimeters away from the wall, but we're still going to only walk half of that distance and half of that distance. Now, of course, in a practical sense, we do arrive at the wall because those tiny distances don't matter in our macro world. But in terms of precise mathematics, if we follow this pattern, we never get to the wall. So this is where limits and convergence come in. The wall is the limit, but we don't get there, and we are converging on the wall. We don't get to it, but we're converging on it. So what we're going to do in this lesson is take a look at mathematical functions and what their limits might be. All right, so let's get a formal definition of a limit using some mathematical terminology. So check this out. A limit is the output of the function, and remember, output of a function is our f of x, not our x, or our dependent variable. So it's the output of a function as the input, which is our x, or our independent variable, as that input approaches a certain value, okay? So it's the output of a function, what's coming out of that mathematical function, as our input approaches a certain value. Now we have notation for that. So check this out. So in an abstract sense, without actually looking at a certain mathematical function, which don't worry, we're going to do that, here's how we write that. The limit of f of x, here's our function, as x approaches some value, which we're calling a right there, equals L, which that capital L stands for what the limit is. So as x approaches this value, which is the independent variable, the input, as the input approaches a, the limit, which is f of x, which is the output, is going to approach a certain value. It's going to be a value, which we use capital L for that. All right, so let's talk about some conditions here. This is the general statement for a limit, but it has an implication that's not immediately obvious. So let's take a look at a little bit more refinement on the notation. So this is true. This function has a limit L as x approaches a, if and only if. That means that this has to be true for this limit to be expressed in this way. And so what we're saying here is the limit as x approaches a from the positive side. So say a graph, we're coming in from the positive side. If that's the same as the limit as we approach a from the negative side, coming in on a graph from this way, if they are the same in that they equal the same L, then we have this limit, then it exists. So we have to evaluate our limits from both sides. At a later time, we'll look at one-sided limits because they are useful for certain things. Okay, one of the ways we evaluate limits is with a table. So here's a very simple limits problem. What is the limit of 2x plus 1 as x approaches 1? So watch this. All right, take a look at this table. I left the important one blank for the moment. So check it out. What we're doing is over here, I'm approaching 1 from the left. So I put in 0.5, I get 2. 0.5 into my function gives me 2. Then I put in 0.75, and that gives me 2.5. I'm going to try 0.9 into my function, I get 2.8. So you can see, it looks like I'm getting closer and closer maybe to 3. Now check it out from the other side. If I put 1.5 into my function, I get 4 out. If I put 1.25, so I'm getting smaller, I'm decreasing to get closer and closer to 1. 1.25 gives me 3.5. 1.1 gives me 3.2. Now, check this out. I can actually put 1 into my function. So if I put 1 in there, I'm going to get 3 out. So the limit of this function as x approaches 1 equals 3. So the point here is to see in the table how as we approach 1 with our x value, our y value is approaching 3. Now this function is straightforward because actually the quick way to do this is I can just put 1 in my function and I'll know what my limit is. But there are plenty of functions where you can't do that. So let's look at one. So take a look at this one. What is the limit of x squared minus 1 over x minus 1? Now check this out. As x approaches 1, I can't put 1 in here because then I'll have a divide by 0 problem. So I can't analyze this limit by what we call direct substitution, which is where I just put that number right in my function and see what I get. It's not going to work. I'm going to have an undefined function. So what I want you to do is pause the video, make a table like we did on that last one, and see if you can figure out what this function is approaching as x approaches 1. So here's my table. I'm approaching 1 from this side, 0.8, 0.9, and I get, when I put 0.8 in, I get 1.8. When I put 0.9 in, I get 1.9. I had to write undefined there because I can't do this one. I can't put 1 in there. And then also approaching from the positive side, from the right side, I'm getting closer and closer to what looks like it's gonna be 2. So using this approach, I think my limit is probably 2. Now, let's just do a test. Try 0.99 and try 1.01 and see what you get for your f of x values. So when I do that, I'm getting behavior that kind of I would expect from looking at this table already. 0.99 in for x gives me 1.99 for f of x, and in a similar way, putting in 1.01 for x gives me 2.01 for f of x. So what is the limit going to be for this function? If you said 2, you're right. It's getting closer and closer to 2. From this table, we can infer that the limit of this function is 2. Now there's another way to do that. And if you want to get a jump on it, go ahead and put this function into your calculator and see if you can figure out what the limit might be. So I graph this on my calculator and I get this straight line. Now in my graph here, I drew an open circle because this function is undefined when x is 1. Your calculator is not going to do that. So you have to kind of think about it. If you look on your calculator, you can just go, well, x is 1. You can roll on up there and you can figure out what your y is. So that's 2. So as x approaches 1, your limit is 2. Now, check this out. Here's why your calculator doesn't put an open circle there. This function on the top, x squared minus 1, is just a difference of squares. So it can be rewritten as x minus 1 times x plus 1, and then of course we're over x minus 1. So this cancels out, and our function really is just f of x equals x plus 1. So that's also an algebraic technique you can use to evaluate a limit. If you can factor and cancel, sometimes you can get rid of your divide by 0 problem and evaluate your limit just by substituting the x value into your function. Second topic in our limits introduction, limits at infinity. And we're going to take a look on the next board. We're going to look at asymptotes because these are asymptotes. So here's the central question though. What are the limits when f or f of x approaches infinity? So let's check that out. The 1 over x function will help us see that nice and clearly. So here's our first question. What is the limit of 1 over x as x approaches infinity? In other words, as x gets bigger and bigger and bigger and bigger forever. What's the value of 1 over bigger and bigger and bigger forever? Think about what's happening there. What is the limit? You could just do this as a critical thinking step. As the bottom of a fraction gets ginormous, what is the value of the fraction going to be? It gets smaller and smaller and smaller. It will never be 0. It will always be some number. But 1 over 10 billion quadrillion is a very, very, very tiny number. So what we are doing is we're approaching 0. So 0 is the limit. This is like going halfway to the wall every time. We're getting closer and closer and closer, no doubt, but we never get there. So in this case, the limit as x approaches infinity of 1 over x is going to be 0. Now, check this one out. What is the limit as x approaches 0 of 1 over x? This is a little different. We're not approaching infinity, we're approaching 0. So evaluate this little fraction in the same way we did this one and figure out if you could tell us what the limit is going to be. Okay, so check it out. As the bottom of a fraction gets more and more tiny, like 1 over 0.000000001, that number is going to be huge. If you divide 0.0000 forever into 1, you're going to get a very large number. So you can't get any, put it this way, there's no limit to how large you can get, so the limit is infinity. Okay? So these are two ways that infinity can come in to our discussion of limits. Now, what I want you to do is pause the video and put in 1 over x in your graphing calculator or Desmos or whatever tool you use to graph, or if you want, you can make a hand graph, and graph that function, and then take a look at how those limits show up on the graph. All right, I sketched a hand graph for us on that. Let's take a look. Okay, let's take a look at how that graphs out. I've done a hand graph for you on the board here. Let's just take a look. So here's my function. It's this curve here. That's how it looks in the calculator. I didn't put any numbers on my axes because I know pretty much that's how that graph looks. We don't need numbers for this discussion. So check this out. As x is approaching infinity, that means the x value is getting bigger and bigger. We're going further and further to the right. Y is getting closer and closer to 0. So it's getting closer and closer to this line, y equals 0. That is a horizontal asymptote. Because this function is really simple, 1 over x, the x-axis is the horizontal asymptote. That will change in a minute. But right now, our horizontal asymptote is the line y equals 0. And guess what? That's our limit, right? Back from here, when we let x get super huge, approaching or going to infinity, our limit is 0, and that is a horizontal asymptote at y equals 0, right there. Now, notation-wise, we use y equals k when we don't know what that limit might be. In this case, it's y equals 0. Now, let's take a look at the case where x gets tiny. That's this one here. X approaches 0, then the y value is getting bigger and bigger and bigger and bigger. So as x gets more and more tiny, y keeps approaching infinity. So that gives us a vertical asymptote. And again, because this function is super straightforward, that vertical asymptote is the y-axis, which is the equation x equals 0. Now, like here where we say y equals k, with the vertical asymptote, we use c as our variable. We don't know what the asymptote is. Now, I want you to pause the video. Your graph, if you did it on a calculator, has something else going on. Take a look at that and see if you can interpret it in the same way. So, your graph on your calculator also gives us this part, because we can put negative values in for x, and we can put x can go to negative infinity basically, and x can approach 0 from the negative side. So that's okay. Now this fits with our definition of a limit because it approaches the same value from both sides. So if we're approaching infinity from the positive side, we're going out this way, y is approaching 0. If we're approaching infinity from the negative side, that's getting more and more and more negative, y again is approaching the same value, it's approaching 0. So this horizontal asymptote governs both curves of our rational function of our 1 over x. Now y is a little different in this case. As we approach 0 from the positive side, we're getting into positive infinity. But as we approach 0 from the negative side, we're going down to negative infinity. So the value of the function is not approaching the same number from either side. So to make this true, we have one thing we need to add, and that's this. Okay? Or we could do it differently. We could get rid of the plus there, and we could write plus minus there. Okay? But if we don't do either of those things, we're implying that as x approaches 0, where f of x, which is 1 over x, is approaching positive infinity, and that's not true. So we need to make that exception here in this case. One last problem. So here we are. We have another rational function. These are the ones that generate curves and asymptotes. So most commonly, you're going to have your more complicated limit calculations dealing with some of these. So check it out. 2x over x minus 1. What is the limit as x approaches 1? Okay, can't plug 1 in there. I'm going to have a divide by 0 problem. So you can make a table or you can make a graph. I'm going to go ahead and do the graph. Pause the video, put this in your graphing display calculator, and see what you get. Okay, so this one bears a little thought. Okay, what I did is I went and did my calculator. I got my curves. I could see what my asymptotes were. So a pro tip for sketching your graphs is draw your asymptotes first, and then it's pretty easy to make the curves fit in the right places so that they approach the asymptotes on the top and the bottom. So here we go. This one generates an asymptote of x equals 1. That's from here. We change the sign. And the y equals 2 asymptote comes from up there. That's our asymptote for y. So now, as x approaches 1, there's something going on here. Is there a limit or not? Okay. If you noticed that as x approaches 1 from the left, we're going to negative infinity. And as x approaches 1 from the right, we're going to positive infinity. That was a good observation. So if I change this question to say, as x approaches 1 from the positive, then this would be positive infinity. Okay? If x approaches 1 from the negative, then this is negative infinity. So that's how that works. Second question. Do that one. Now this one, as x approaches infinity, you can do this just by looking at the function using the same analysis we did last time, but it also shows up on the graph. Okay, so looking at the function, we can see we get an infinity here and infinity there. If this is like a ginormous number, the fact that this is minus 1 is not really going to matter a whole lot. If this is 500 billion and that's 500 billion, this is going to be twice 500 billion. So using that analysis, we can go, yeah, this is probably 2, because whatever on the bottom, this is going to be twice as big on the top. So that's going to reduce down to 2. However, the graph is really good. It shows us exactly what's happening. As x approaches infinity, that would be as x goes out here all the way to infinity, y is dropping down, getting closer and closer to this asymptote, which is 2. So that gives us our solution. Now I want you to pause the video and determine if we're approaching the same number from the left and the right. So as x approaches negative infinity, are we also approaching 2? Because if that's true, this statement is correct. If it's not true, we need to make a little edit here to make sure that it is correct. So pause the video, do that, and come back. So it is correct. As x is approaching negative infinity, we're going further and further negative. We're still coming up to this line where y is 2, or where f of x equals 2. So this statement actually is true as we approach infinity from either side, which is what implies there, because I don't have a plus or a minus, the result is the same. Our limit is 2. Now that you've watched the video, take a moment to jot down any questions so you can bring them to our next class. Remember that you can always watch the video again to deepen your understanding. If you enjoyed the video, please click like or subscribe.